This is the first of 3 videos that we're going to do on least squares. In this video, we're going to talk about least squares for matrix problems. That is, we're going to go over the linear algebra of least squares. In the second video, we'll talk about the most important application, which is linear regression. And in the third video, we'll talk about multiple regression and about other kinds of curve fitting. So, we are always working in Rn with a standard inner product. And what do you do if somebody hands you a problem, ax equals b, and says, can you find a solution? Well, we studied this a long time ago, and we saw that all of the things that can be written as ax, they're linear combinations of the columns of A, and therefore they're in the column space. So this has a solution if B is in the column space, and it doesn't have a solution if B isn't in the column space. Okay, so what do you do if B isn't in the column space? And there's an obvious answer, namely to give up, because there is no exact solution. But for many real-world problems, there's a better answer. The better answer is fudge it. Find the value of x. You can't make ax equal to b, but you can try to get ax to be as close to b as possible. And this is called a least squares solution to our problem. So let's see how that works. Let's look at an example. Suppose I gave you these 4 equations. Now, you'd look at that and say, there is no solution to these 4 equations, because after all, looking at these 2 equations, you subtract them from each other and you get that x2 is 0. And if x2 is 0, then x1 has to be 1, but x1 also has to be 3, and x1 has to be 3, and x1 has to be 5. This doesn't make sense. The equations contradict each other. And you might be tempted to just take the first 2 equations and solve those first 2. Or maybe take the first and third equation, or the second and fourth equation. But it's usually not an idea to try to get 2 equations to match perfectly at the expense of making the other ones way off. Instead, we'll try to make the sum of all of the errors be as small as possible. So here is b minus ax, and we want to make this vector as small as possible. So the squared length of this vector is the first component squared, plus the second component squared, plus the third component squared, plus the fourth component squared. Since we're adding squares, that's why we call this a least squares problem. And how do you minimize the sum of squares? Well, you can do it with calculus. You can take a derivative, set the derivative equal to 0, solve some equations that way. But it's much more elegant to do it with geometry. We will not do any calculus in this problem at all. So here's a picture of what's going on. We've got our vector b, and it's not in the column space. And we want to get ax to be as close to b as possible. Well, we can get to any point in the column space. And which point in the column space is closest to b? Well, it's the perpendicular projection. Any other point is going to be farther than this distance. So you want to solve ax equals the parallel part of b. In other words, you want to throw away the perpendicular part of b. This is an error that you've got no matter what value of x you pick. You want to at least get directly under b. So if you solve ax equals b parallel, that minimizes the distance between b and ax. Now here's the really cute trick. If you write A as a bunch of columns, you look at each column separately and you think of each column as a vector. If you compute A transpose times B perp, well, A transpose is a bunch of rows. A1 transpose, A2 transpose, A3 transpose, AK transpose. And A1 transpose times B perp is the inner product of A1 with B perp. And A2 transpose times B perp is the inner product of A2 with B perp. And AK transpose times B perp is the inner product of AK with B perp. This is why this method is restricted to Rn with the standard inner product, where the inner product of 2 vectors is the transpose of one times the other. But B perp is perpendicular to everything in the column space. And A1, A2, A3, and AK are all in the column space. So this has to be 0, and this has to be 0, and this has to be 0, and this has to be 0. So whenever you take A transpose times B perp, you always get 0. So here's how we solve our equations. We want to solve AX equals B parallel, which is B minus B perp. We multiply both sides of the equation by A transpose, and we get A transpose AX equals A transpose B minus A transpose B perp. But A transpose B perp is 0. So lo and behold, we have the equations A transpose AX equals A transpose B, and this allows us to solve this problem without ever figuring out what B parallel is or what B perp is. We just need B, and the magic of A transpose is that it captures the essence of B parallel. So what we've just shown is that if you have any kind of least squares solution to AX equals B, which is to say a solution to AX equals B parallel, it's automatically a solution to the equation in the red box. And likewise, every solution to the equations in the red box give you a least squares solution to AX equals B. And to see that last part, let's suppose we have a solution to A transpose AX equals A transpose B. Well, that means that A transpose B minus AX has to be 0. But that means that B minus AX has to be orthogonal to A1, A2, A3, A4, and so on. So it's orthogonal to everything in the column space. So we can write B as AX plus something orthogonal to the column space. This is B parallel, this is B perp, and we solved our problem. So now that we got the theory is always solve this equation. We can put a box around it, we can put a star next to it, put another star next to it. That's the equation you always want to solve. And we can go back to our example. In our example, A was 1, 1, 1, 1, 1, 2, 3, 4. And A transpose is the same thing written as rows, and here's B. And if you compute A transpose A, you get this row times this column is 4, first row times second column is 10, second row times first column is 10, second row times second column is 30. And A transpose B is 1236. We've seen this problem before. The solution to these equations is 0, 6/5. In fact, you can see that 1236 is parallel to 1030. And so we get that AX is 6/5, 12/5, 18/5, 24/5. And the residual, the thing that's left over, is minus 1/5, 3/5, minus 3/5, 1/5. And that's orthogonal to 1, 1, 1, 1, because these terms add up to 0. And it's orthogonal to 1, 2, 3, 4. You can work it out. And this is what we call B perp. Okay. Now I said that all along we were working only in Rn and only with the standard inner product. Now I'm going to take a minute to tell you how to deal with other cases. If you were dealing with Cn with the standard inner product, then we wouldn't take inner products by taking a transpose times y. We would take a transpose conjugate times y. In which case, you don't take the transpose of A, you take the transpose conjugate of A. But otherwise, it works the same way. If we have Rn or Cn with a non-standard inner product, this may happen if you trust some of your data better than other data and you want to give them more weight. Then to take inner products, you need a metric matrix. And the way you take the inner product with all of the elements of A is you take the transpose conjugates and multiply the metric matrix. So you start off with AX equals B, take the inner product with all the columns of A, and that's your equation. In all cases, what you're really doing is you're taking the inner product of AX with the columns of A is equal to the inner product of B with the columns of A. That gives you a bunch of equations that you then have to solve.